This is where we had stopped. We had written an expression for energy of helium atom in terms of the spin orbitals and the Hamiltonian. Actually, I should have written it using PowerPoint like I do, but then it is too tedious. So, I decided that I should subject you to my bad handwriting at least once, sorry about that. Now, let me do something, let me try and expand this a little bit, not all, little bit. So, let me, what are we trying to do here? We are trying to say what is the role of the spin part of the wave function. We have already given you the answer, the expression for energy, but there was no spin part, only the spatial part of the orbital was there. So, we are going to convince you now that that is okay. We can take care of the spin part, or rather the spin parts sort of take care of themselves, we will see how. Now here when we expand, what will the first term be? For the first term I can take this and H1 and this. So the first term is going to be something like integral phi 1 alpha 1 phi 1 beta 2 H1 operating on the same wave function phi 1 alpha 1 phi 1 beta 2, plus there will be more terms, we will perhaps write 1 or 2 of those. But before that, let me try to see and let me try to make sense of this integral. So remember, this integral is really not a single integral, right. So what are the parameters here? There has to be something in terms of there has to be dr1, there has to be dr2 and there has to be ds spin also, okay. So it is actually a triple integral. So in principle I should be able to separate it out into a product of maybe 3 integrals. Can we do that? Let us see. So first of all I can take the spin part out. I hope you understand what I am talking about. This here is really integral, 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 whatever we have in terms of dr1, dr2, ds I can say. So I want to write it as integral of the spin part ds multiplied by integral of the r1 dependent part with respect to dr1 and integral of the r2 dependent part dr2, okay. It is just that we are using bracket notation, nothing else. So we can take the spin part out and write an integral for itself, that will be integral alpha 1 star alpha 1 over all space, that is gone, because remember what is this phi 1 alpha 1, it is really phi 1 1 alpha 1, that means electron number 1 has alpha spin and resides in spatial orbital phi 1, okay. This has gone out. Next, what do I have? In the spatial part also I have coordinates of your well no, I mean that is all, there is one more, not spatial part. I have another spin part, that is beta 2, yeah, beta 2 and beta 1, beta 2 and beta 2. My handwriting is so bad that I myself am getting confused. So I can blame you for getting confused here, sorry about that. So this is what we are talking about, beta 2 and beta 2. So second integral that comes out is beta 2, beta 2, beta 2 in bra, beta 2 in ket. What remains the spatial part is phi 1 1 H1 operating on phi 1 1. How did I get this phi 1 1? From here. Let us not forget that what we have written here, this phi 1 alpha etc., these are spin orbitals. So they are products of a spatial part and a spin part, right. So I have to write 1 in brackets in both, okay. So now just look at these integrals. spin wave functions are normalized. This is equal to 1, this is equal to 1, and this, what is this? This is equal to I, yeah, j equal to 1, Rj, this small j is equal to 1, minus del j square by 2 minus z by Rj, this is equal to H1 as we have defined, then that operates on phi 1j. So, this is basically I1. So, the first term, remember we are only writing the first term now, first term becomes I1 from here, neglecting the, we are not really working with the normalization constant, we are just working with the remaining wave function, that is fine. Okay, so you see that we are actually getting those integrals which do not contain the spin parts. The spin parts sort of take care of themselves by normalization, right, normalization, that is all. Now, what more can we do here? Let us take something else. What is the second integral going to be? Second integral is going to be say I will take this one, minus phi 1 oh no, what am I writing here? So, we will write here. So, second one will be minus phi 1 alpha 2 phi 1 beta 1 H1, then I will take this minus. So, minus minus it will become plus, and the integral will be something like phi 1 alpha 2 phi 1 beta 1. What did I say I will take, H1 or H2? Let us take H1. H1 phi 1 alpha 2 phi 1 beta 1. I hope it is not very difficult to see that by similar treatment we are going to get I1 once again, right, because what do you have? You will have phi 1 1 H1 phi 1 1, the same thing. Again you have alpha 2 that is 1, beta 1 that is 1. So, again you will get I1 from there. Okay. So, you see how this expression I1 comes in this in the expression for how this integral I1 comes in the expression for energy. Okay. Now, let me clear this up a little bit. Well, all the terms are there, I am just not writing all the terms, I am trying to just expand and see what happens. Now, let us take a different combination of terms. We have already written two terms, so I can write something dot 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 plus dot 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 what we have got I1. Third one, let us take this, let us take H1 and let us take the second term, because that also has to be done, right. A plus B, well, A minus B into A minus B, how much, what is it? Yeah, A square minus AB minus BA minus B square, that is the kind of thing we are doing here. So, what will that integral be now? Plus integral alpha phi 1 alpha 1 phi 1 beta 2 H1, and now I am taking the second one. So, see, this will not be plus, this will be minus, and the second one is phi 1 alpha 2 phi 1 beta 1. Now, let us see if things get more interesting. So, I am not writing the first terms, whatever terms are there, only this term I will focus on. What will happen? I can bring out phi 1 1 H1, then phi 1 2, right. So, what I get here is, well, even before going there, here we have alpha 1 and here you have beta 1. So, you get alpha 1, you get beta 1, multiply them together and integrate over all space, what do you get? You get 0 because they are normalized. So, what I am trying to say is that lot of these terms actually become equal to 0, right. And then when you go a little further, when you expand upon this Rij term, you are going to get what is called this Jii, J11 term, I equal to J here. So, there is no problem, you just can take this J11, right. So, this is how you can expand. See, just for helium it is so long that we are not having the patience to work it out. So, imagine what it will be for an n electron atom where n is a large number, it is going to be huge. But we just demonstrated, I hope this demonstration was not confusing for you. You just try to work it out yourself, you will be convinced that you will be able to write the expression of energy in terms of these integrals. Okay, for helium what happens? For helium, first of all I will write this I1. So, I1 plus I2, but I1 plus I2 are one and the same, right. So, you can write what expression you get from there, and here you will write Kij equal to Jij, where, well, again I and J are 1 1. So, you can write 2J11 minus J11, that will be 1J11, and then you can substitute, you will get the expression for energy for helium. But the story does not stop here. We have learned variational method. So, we know that this expression that we have got, now we have to minimize, we have to find the minimum value of the energy that we get from this expression, right. How do you do that? In variation method you just minimize it, right, and when you minimize you end up getting equations like this. You get a Fock operator, this is called a Fock operator. I will show you the form of Fock operator, or maybe I will not, I will tell you what Fock operator is made up of. If you want to know the form, you are welcome to consult Macquarie's book or Pillar's book, it is written there. Well, Pillar's book I am not very sure, Macquarie's book definitely. So, Fi operating on phi I gives me epsilon I phi I, that is the kind of equation that we will get. Okay. So, these Fi's are made up of these integrals. Essentially it is something like an expression analogous to the expression of Hamiltonian, but with the functions in it, you just expand it. And how many n values are there? There are well 1, 2, 3, 4, 5, 6 up to n I values are there, not n, right. So, that is the number of orbitals that are there. Okay. Remember we had said that we have n orbitals and we can put in maximum of 2 electrons in them. So, we can accommodate 2 electrons in this n number of orbitals. So, what we get then is this kind of equations using Fock operator. So, again this is like an eigenvalue equation. Fock operator operating on a wave function gives me back the wave function multiplied by epsilon I get n number of equations, and these are n coupled equations because these wave functions are not really independent of each other, are they, right, they are not. So, what do you do with these n coupled equations? You solve them numerically by using your self consistent field method. What is the initial guess value that you use? The initial guess value that you use is of your linear combination of Slater determinants. So, essentially what you do here is that you write this expression, get Fock operator. How do you get Fock operator? Because Fock operator will also contain these phi's, remember. So, it is not a simple differential equation, it is exactly, well, very similar to what we have done earlier. So, to generate the Fock operator you need the guess values, and the guess values that you get are linear combinations of Slater equations. I thought I have them written below here, looks like I did not write, sorry about that. So, you start with the Slater determinants, start with orbitals, start with hydrogen atom orbitals, okay, Slater determinants involving hydrogen atom orbitals, and construct the Fock operator. Let the Fock operators operate on the wave functions and write down the n coupled equations, solve them numerically using the self consistent field method. Then you get the next set of Fock operator of these wave functions, use these wave functions to generate the next generation of Fock operators, and then go on until self consistence is obtained, and once again this becomes a computational problem. Okay. That brings us to an end of the discussion that we wanted to perform, and let us not pretend that we have discussed everything. That is way beyond the scope of this course. In fact, the course has become much more than what I initially intended it to be. So, we are not going to go into further detail. Let us hope that we will be able to have another NPTEL course on advanced topics in quantum chemistry. If you are successful in that, then we will start from here and talk about more advanced methods, because you might remember I told you that a practitioner of quantum chemistry once told me that for him quantum mechanics begins where Hartree-Fock ends. But for the purpose of this course it ends, well, at least for atoms it ends where Hartree-Fock ends. The reason for doing this discussion in the first place is that we wanted to make certain points which are useful not only for these many electron atoms, but also for molecules. Remember, the course is quantum chemistry of atoms and molecules. So, the points that we have made in this discussion are these. First of all, you have to use approximation techniques, and the techniques we have learned are perturbation theory techniques and variation methods. Using variation method you can get upper limits of energies. Using perturbation theory you can actually do an accurate calculation if you go to high level higher order perturbation correction terms, and provided the perturbation does not change the system too much from the ideal system. And the problem here is that there has to be a system for which an exact solution of Schrodinger equation must be there. That requirement is not there in variation method, that is why it is so popular. But then you cannot do it at one go for most of the systems. For initial systems that we tried, for systems where we knew the exact solutions, we did them at one go. But then gradually we learned that the only way out, the only way to tackle the problem of many electron atoms and systems as complex as these is to resort to iterative techniques, and the techniques that you use are called self-consistent field methods, in which you guess a wave function, you construct an effective potential using those guess values of wave function, then find the solution of that equation. Because the problem, remember, even though I am saying it many times, I will say it again, the problem with this kind of approach, Hartree-Fock approach, is that the operator itself contains the function. So, unless you start with some kind of a guess value of function, you cannot really get going, right. So, to get going we give some guess value, and that guess value, or that guess cannot be any guess, some sort of sense has to be there in the guess, but eventually we have learned that we do not have to stick to the exact solutions at all, we can take anything. So, Gaussian, exponential, many things, we talked about different kinds of orbitals. And finally what we have shown you very sketchily is that by using this kind of SCF calculation, using Hartree-Fock method, using variational method, one can get, one can try and solve, get energy values for complex many atom systems. What I am not going to say, but I request you to read from Macquarie's quantum chemistry book or Prasad's book or Chandra's book, any book that you like, is what we have actually studied in class 11-12. Remember, for many electron atoms we had talked about variation of ionization energy, sawtooth variation. We had talked about variation of electronegativity, so on and so forth. Actually, when you do this kind of an SCF calculation, you get results by which you can get very close to the experimental values. So, this sawtooth variation where you see signatures of this main shell and subshell, that can be actually modeled very nicely using Hartree-Fock method SCF calculations. So, I would like you to read that part, because that is just story, more of a story than what the story I have told you over the last 2 modules. So, please read those by yourselves and refresh your memories, and also understand to a little better extent, I hope, why you get that kind of a trend for many electron atom. We are not going to discuss that explicitly here. Okay. That brings us to an end of this part of the discussion. That brings us to an end of the discussion of atoms. But the concepts that we have generated here, exchange integral, Coulomb integral, okay. And remember something called S, integral of phi I phi j over all space. All these integrals are going to come handy in the subsequent discussion that we are now going to perform on quantum chemistry of molecules. And there we are going to talk about two approaches, valence bond theory, molecular orbital theory. I suspect all of you have heard of all this, it is just that we hope that we will be able to take our understanding to like one notch higher, not complete, but one notch higher than whatever it is at the moment, right. So, next day we start talking about quantum chemistry of molecules.